Afternoon, everyone. I'd like to thank the chair for the introduction. Today we're going to talk about microacoustic shear horizontal lithium niobate leaky source for harsh environment sensing. As a brief outline, of course, we have our background and motivation. Then we're going to cover the fabrication and design of the resonator, as well as a proof of concept application, which is a microviscosimeter. Harsh environment sensing has become a crucial application in modern technologies, especially for instances like oil rigs or heavy-duty machinery, as well as improving the efficiency of everyday applications such as car engines, and who knows what the future holds for us. Of course, the requirements are for robustness, as the devices are often immersed in high pressures and temperature, corrosive chemicals, direct flames, and radiation. And of course, we need high performances in terms of sensitivity and quality factor and frequency selectivity. For this reason, piezoelectric MEMS resonator are an ideal candidate as they present overall good performances. They're generally compact and cheap. However, they usually have limitations, especially thin film resonators are fragile, and for instance, it's not a good idea to employ them as suspended structures in contact with hot viscous fluids. Additionally, electrodes materials such as aluminum, which is very commonly used in soles and LVRs, have low melting points, are easily corroded, and do not handle power very well and suffer from electromigration, as we can see in the top right. Finally, traditional SOs have low coupling, which ultimately limits their applicability. As I said at the beginning, our case study is a microviscosimeter. Traditionally, oil sensors are either capacitive and measure the electric constant of the oil, or optical to detect the presence of particulate. However, there is no straightforward way to measure viscosity in situ. For this reason, we propose a lithium niobate shear horizontal leaky acoustic wave resonator that leverages high piezoelectric coefficient and quality factor, as well as a very high curie point. In this case, we're employing corrosion resistance electrodes such as aluminum and tungsten. And this works because of the unique way that the mode shape is configured. In particular, we see that the whole of the displacement is in the electrodes, which means that their motion will be impacted by changes in viscosity of the surrounding fluid. Moreover, this resonator is very cheap to fabricate, as it only constitutes of 2 masks. Moving forward, the first step is, of course, to optimize the coupling coefficient. Lithium niobate is anisotropic, therefore its properties depend on the Euler angle orientation. And here we can see the numerically evaluated coupling coefficient as a function of the Euler angles of rotation, as well as on the right, a focus on commercially available cuts. Additionally, the coupling coefficient also depends on the electrode configuration. In particular, only specific combinations of material and thicknesses are necessary to achieve high performances. To leverage leaky source, we need dense and stiff electrodes with an optimized ratio between the thickness of the metal and the wavelength of the resonator. This is so to confine the energy at the interface while reducing the stress in the electrode, which is a known cause for metal losses that ultimately impact the quality factor. Using COMSOL simulations, we derive the dispersion curves for the coupling factor for X, Y, and Z cut. And we can see that for both gold, platinum, and tungsten, we can find a maximum that maximizes the electromechanical coupling. For our design, we chose an X cut with a lambda of 6 microns, which should give us around 500 megahertz of resonance and a thickness of the metal at 300 nanometers. This design was optimized for the gold, but we still try to fabricate tungsten devices with an extra mask required to cover the pads to reduce the ohmic losses in the contact. After fabrication, we have a direct RF probing preliminary measurement of the devices, and we can see very good quality factors and coupling. And in particular, if we look at the tungsten device, we see larger coupling but lower quality factor. This is because we employed lift-off process that necessarily uses low temperature deposition, which produces beta phase for the tungsten. whereas alpha phase is much less resistive but requires high temperature, thus making it impossible to perform the liftoff. We also see some transverse spurious modes that can only be optimized through optimization of the fingers. Subsequently, we perform power handling measurements, and we can see that there is basically no degradation in the response from minus 20 dBm to plus 15 dBm, and the tungsten device is still viable at 20 dBm, while the gold a little bit is gone, but it is to be expected. Crucial for us is the temperature response, and in particular, using a heated plate on our probe station, we change the temperature from 20 degrees C to 200 degrees C, and we perform measurement in steady state conditions to extract the temperature coefficient of frequency in the linear approximation, and was found to be minus 65 ppm Kelvin for the gold and minus 67 ppm Kelvin for the tungsten. These two values are very similar because the configuration of the device is the same. However, since this value is modal and there is a slight difference between the tungsten and the gold, we see the slight difference. Finally, as we're targeting harsh environments, we exposed the chip to a direct butane flame for 60 seconds at around 900 degrees C. And as we can see in the plot in the right, we have basically no degradation in the response of the gold device. Lithium niobate is indeed paraelectric. However, in this case, we're using very small chips, and besides this ultimate resiliency test, in our application, we do not expect any abrupt change in temperature. Therefore, the paraelectricity effects should be minimal. And as a matter of fact, even though we shifted the temperature from 20 to 900 degrees, the chip survived, both the resonator and the chip itself. These preliminary results are very, very encouraging, and they led us to develop a proof of concept viscosimeter. The viscous damping is a very, very complex phenomena, but in the first approximation, we can assume that the quality factor due to the viscosity is inversely proportional to the value of the kinetic viscosity itself. And in this case, we used fumbling oil from YLVAC, and we can see the dispersion curve for the kinetic viscosity as a function of the temperature, which is in turn inversely proportional to the temperature. Neglecting other sources, we can summarize the total contributions to the quality factor as the inverse sum of the intrinsic losses that are due to the resonator and the viscous quality factor. Therefore, what we can expect in this very simple, straightforward model is a linear relationship between the quality factor and the temperature. For the testing, we simply wire bonded our resonators, both the gold and the tungsten one, to an FR4 PCB. Unfortunately, very long wire bonds were necessary for this testing, and they ultimately impacted the quality factor of our resonator, but we were still able to measure it. And two sets of measurements were carried out. One for the temperature only, because we need to characterize what's the temperature response by itself. If then it was done via direct RF probing, we wanted to double check once we loaded the resonator with the wire bonds. And then we applied the oil and heat it up. Of course, all measurements were carried out over a very long time range to ensure steady state conditions. And all the results were fitted through MVVD modeling, and the viscous damping and the loaded quality factor were extracted from the motional resistance of our MVVD model after de-embedding the effect of the ohmic losses, which was very small, having used gold and tungsten, which have very low resistivity. Both plots show the relationship between the series resistance and the evaluated quality factor as a function of the temperature. Now, the only thing left is to correlate the data. And as we can see in the plots, we have a almost perfect linear trend for the viscous quality factor and the temperature, and an almost perfect inverse linearity for the viscous quality factor and the kinematic viscosity. But what is most interesting is the perfect agreement between the tungsten and gold resonator, which led us to conclude that these measurements were accurate and validated each other. Of course, in a real case scenery, having such high temperature coefficients of frequency, as I said, minus 65 ppm Kelvin, we would need to perform a differential measurements in which one resonator is exposed to the oil while the other is isolated from the oil, and we can track the temperature shift on the first one while the viscosity can be tracked with the resonator exposed to the oil. To conclude, we successfully fabricated very high performance leaky saws that leverage shear horizontal mode on XCAT lithium niobate with good power handling and a very high temperature coefficients of frequency. And we employed this unique mode shape of vibration to realize a proof of concept viscosimeter for real-time in situ sensing in harsh environments. However, the work is not done. Of course, we need to further optimize the spurious modes, either employing Bragg refractors for the lateral spurious modes and apodization of the fingers for the transverse spurious modes, as well as developing a high temperature readout electronics for on-chip differential measurements with wireless capability. I would like to thank Professor Luca Colombo, who equally contributed to this work, and my colleagues at Northeastern University, as well as the Costas Cleanroom staff at Northeastern and the Arbor CNS staff. Thank you very much for your attention. If you have any questions.